I wanted to go over a few half-life problems. Some of these are from the worksheet that we did in class. I found this graphic on the web and I really like it because it links together two different aspects of half-life. One is, a chemical, a radioactive substance, starts off as one kind of substance, and then over time more and more of the substances changes. So here we have 20 little atoms, and then after a half-life only 10 of those atoms will be the same atom. And then after another half-life, half of those atoms will have changed, so 10 of the remaining have changed, so we have 5 left. And then after that, just a few of those are left. So every time interval, half things go down. So if we started at 100, then after one half-life we would be at 50, and after another half-life we'd be at 25, then we'd be at 12.5, 6.25, 3, and we can see we get this really distinctive kind of a curve, sort of an exponential drop, which is characteristic of half-life. Also notice that for half-life, it doesn't really matter where you start. So if I started at 50, then after one half-life it would go down to 25. And anytime I start, it takes one half-life to get to the next half as much chemical left over. One of our problems was to draw a graph if the half-life was 2 tosses. So let's say we put a dot up here at 100, and we could make a little data table and be time and the number of particles left over. So let's say at time 0 we would have 100 particles. So after 2 half-lives, because it says the half-life is 2 tosses, or after 2 tosses, then we would be down to 50. So we would put a dot in here on 2 at 50. We'd say, okay, then at time 4, that's 2 half-lives, this will have dropped down to 25. Let's plot that point. At 4, we would do about 25. When we get to 6, 8, 10, when we get to 6, the 25 will have dropped down to 12.5. So on our graph, we would say 6 and 12.5, be about there. At 8, that'd be about 6.25. On our graph, we'll just try to find a 6, a little bit more than half. And again, at 10, we would know that'd be about 3.125. But on our graph, we're just going to look for about a third of the way up. And we'd have this kind of a graph. Again, they're very distinctive looking curve. Now we can try a couple of word problems that we have. So this says Lawrencium 257. That is really not an important idea, it's just what the chemical is. But things that are important is the half-life. So that's T1 half, so the half-life is 8 seconds. If we begin with 80, how long will it take until only 5 grams remain? So we would say, okay, we have 80 grams. After one half-life, we would have 40 grams. After another half-life, we would have 20 grams. After another half-life, 10 grams. And finally, we get down to 5 grams. So we draw this picture because of the information in the problem. It says 80 and 5. Now it says each half-life is 8 seconds. So we had 1, 2, 3, 4 half-lives. So 4 times 8, 32 seconds. Whoops. So the answer here would be 32 seconds. For here, again, what this sodium is really not important. Okay, what is important is that we have the half-life. It's 15 hours. And we're going to start with 90. So we know after one half-life we'll be down to 45. After another half-life we'll be down to 22.5. But the question is, how many half-lives should we go? And here we get the answer here, because in this problem we have 75 hours total, and we have 15 hours is one half-life. So if we divide 75 by 15, we find out we have 5 half-lives. So that means we want to do this dividing by 2 5 times. And for this, I think I'll probably have to get out my calculator. So half of 22.5 would be 11.25. That's okay. Then half of that with my calculator is 5.625. And half of that would be 2.8125. And I would kind of round that off since we're really only working about 2 significant figures. 2.8 grams would be a great answer for that. Okay, problem 6. We have 64 grams of technetium 95, and again, we don't really care about the chemical, that doesn't affect the numbers, but we have 64 grams, and it's reduced to 4 grams in 80 hours. So our picture is we start with 64 grams. After one half-life, it would be reduced to 32. After another half-life, 16. After another half-life, 8 grams. So now we've matched, no, it says 4 grams. Alrighty, so that took 1, 2, 3, 4 half-lives. So 4 half-lives is 80 hours. So therefore, 1 half-life must be 20 hours. So our answer is 20 hours. Now, even though each time we're kind of giving different information, it's still the same basic picture that, we start with a number and we go down by 2 each time. And I call those my Scoopy arrows. Number 7. We have a sample of something that decays to 6.25% in 18 days. Now, 6.25% of its activity, I mean, if we put a Geiger counter next to it, we hear all the little clicky sounds, and it goes down to only 6.25. So implied in this is that we're starting from 100%. So if we see percentage, kind of think of our first number is 100. So after one half-life, it'll go down to 50%. After another half-life, 25%. So we're going to keep doing this until we get down to 6.25%, which won't take long. So we can see we have 1, 2, 3, 4 half-lives is 18 days. So what's one half-life? Well, if I divide by 2, then I get 9 days. And if I divide that by 2, then I'm going to get 4.5 days. And that's my half-life. Or I could have just done 18 divided by 4. A sample has a half-life of 15 hours. We need to have 2 grams after 45 hours, so how much must we begin with? So you can see this is kind of a backwards problem. So we have 2 grams that we need, but 15 hours ago I would have had 4 grams, and 15 hours before that I would have had 8 grams, and 15 hours before that I would have had 16 grams. And the question is, how many times do we have to go back? So if I have 45 hours total, and I know that 15 hours is 1 half-life, then that's 3 half-lives. So I've already done that. I've gone back 1, 2, 3. So I would have had to start with 16 grams in order to have 2 grams after 45 hours. Same kind of problem, just working backwards. Now we're talking about lawrencium has a half-life of 8 seconds. How long will it take for 75% of the sample to decay? Now this is just a interesting wording problem. We're doing percents, so we'll start with 100%. But the question is, how long will it take until 75% has decayed? Not we want to get down to 75%, but 75% is gone. So obviously, if we started with 100 and we wanted to wait until 75% was gone, what we're looking for is 25%. So we're starting with 100%. One half-life will get us down to 50%, and another half-life will get us down to 25%. So we're only talking about 2 half-lives. So 2 half-lives times 8 seconds for a half-life. We have a half-life here. I mean, the total time would take 16 seconds. And our last problem, carbon-14 has a half-life of 5,000 years, and we use that to date fossils because everybody has a little bit of carbon in them. A sample is only 3% as radioactive as it should be compared to carbon from a living organism. So the idea, in a living organism, we are constantly bringing in new carbon and keeping our carbon-14 at a certain level. But once something dies, then the carbon-14 just simply goes away. So we would say percentage, we're going to start with 100%. And we know after one half-life, which is 5,000 years, we're going to go down to 50%. After another 5,000 years, 25%. After another 5,000 years, be 12.5%, 6.25%, 3.125%. That's close enough. So we're getting pretty close to 3%. So you see that's 1, 2, 3, 4, 5 half-lives. So 5 times 5,000 is equal to 25,000 years. And that's how we do half-life problems. Now, if somebody said, well, this is not really down to 3, this is 3.125, how do I get to a non-whole number of half-lives? There is a formula that we can use for that. And it's a little bit more complicated, but I'll just mention it in case you want to get into that kind of stuff. And it's the natural log of your chemical at time 0 over your chemical at time t is equal to k times t, and t is the time. And so in our case here, we would say that this top number here is 100%. We'd say our bottom number is 3%. Okay, the time is what we're looking for. And we have this other variable, and that other variable comes from the equation that if we're talking about a half-life, the natural log, the original concentration could be any number divided by half of itself. So if we started with 100, we would have gone down to 50. That would be 2. If we started with 2, we'd gone down to 1. If we started with 10, we'd go down to 5. Anything. So it's always going to come out to be the natural log of 2 equals k times the half-life. So we're saying this first equation here, the special case of half-life, this is true, and the natural log of 2 is a constant. So it's 0.693, if you do it on your calculator, is equal to k times, in this case, 5,000 years. And what we would do is solve for k, and it would be in years to the minus 1. So that would give us a value of k. We substitute back in, and we could calculate the time. A little complicated, but that's how you would deal if you really wanted to know what it was at 3%. And we can see it's going to be a little bit longer than 25,000 years.